Okay, so here we go. This is the practice test for Solutions, Unit 9. Which of the following would increase the concentration of a solution? Well, you can increase the concentration of a solution in a couple ways. One would be to add more solute, or the other way would be to remove some of the solvent, and allowing solvent to evaporate would be one way to do that. Increasing temperature and placing a lid over top of the solution wouldn't have any effect, and adding more solvent would actually dilute the solution, lowering the concentration. Which of the following cannot form a solution? Well, a solid solute in a gas solvent is going to form possibly a suspension or a colloid, but not a solution. All of the other combinations are possible solutions. The Tyndall effect is a property of colloids. Colloids have medium-sized particles. The particle size are in the nanometer range, which is the same range as visible light. So the ability of colloids to scatter light is called the Tyndall effect. So one way to distinguish between a colloid and a solution is to shine light through it. Colloids will scatter the light, whereas a solution will allow the light to pass through. What is the molality of a solution in which 15 grams of HCl, hydrochloric acid, are added to 150 milliliters of water? Well, so we need to remember that molality is moles of solute per kilogram of solvent, which means that molality, we need moles, and moles is grams divided by molar mass. So in this case, we've got 15 grams of hydrochloric acid. The molar mass of hydrochloric acid is 36.4, which means that we have 0.412 moles of sodium chloride. 0.412 moles divided by, since we're talking about water, the number of milliliters is equal to the number of grams. 150 grams is 0.150 kilograms, so this is moles per kilogram. And when we do that out, we get 2.75 molal as the concentration. 1 mole of which compound would lower the freezing point of water the least? So the smallest effect will be given by the substance that's going to produce the smallest number of particles in solution. And anytime you've got potassium with anything, it is going to dissociate into multiple parts, which means the I value will be equal to some number greater than 1. So for B, that would be 4. For C, it would be 3. The I of C would be 3. The I of D would be 2. The only one here that is not an ionic compound that's going to dissociate is the sugar molecule. Okay, anything that says molecular or non-electrolyte, or if it's got carbon in it, all those types of compounds are going to have an I value equal to 1, which means they're going to have the smallest effect when you put them into the colligative properties formulas. Adding solute to water will decrease or lower which of the following colligative properties? It will lower the freezing point of water, it would raise the boiling point, have nothing to do with solubility, nothing to do with specific heat. The other property that could be lowered would be the vapor pressure. Lowering the vapor pressure is what leads to higher boiling point, but in this case the question was which of these, and the only one there that would be lowered is freezing point. Decreasing the temperature of an aqueous solution will do what to the solubility of gas and what to the solubility of a solid? Well, one thing you need to remember is that gases and solid as solutes generally have opposite effects with temperature. So whatever one does, the other one's going to do the opposite. So since we're decreasing the temperature will increase the solubility of a gas, okay, which means it decreases the solubility of a solid solute. Right? Solid solutes are dissolved by collision with solvent particles, so decreasing the temperature slows down the particles. They have fewer collisions. The collisions themselves have less energy, which means they're not going to dissolve as much. So it decreases the solids. Decreasing the temperature likewise lowers the average kinetic energy of the gas particles, which makes them less likely to escape from the solution, so it actually increases the solubility of a gas. Increase in temperature, of course, would have the opposite effect. Increasing temperature lowers the solubility of gases and increases the solubility of most solid solutes. Pressure of a gas solute is reduced by half. How does that affect the solubility of gas? So pressure can affect solubility of a gas, and pressure is directly related to pressure. It's directly proportional to the pressure above the solution. Proportional. So that means basically whatever happens to the pressure above the solution, you're going to have the same effect proportionally on the solubility of a gas. Okay, so if the pressure is cut in half, pressure is being lowered, which also means that the solubility of the gas is lowered. And if we're cutting the pressure in half, we're decreasing the solubility by a factor of 2. Okay, so we're going to make a phase diagram, and the scale on this one turned out to be a lot trickier than I intended. The scale on the actual test will not be as difficult to draw as it is in this practice problem. But here's what you need to remember. There's triple points, boiling points, melting points. There's also a critical point on a phase diagram, and the lines on a phase diagram show the transition points between solid, liquid, and gas phases. So the first thing we're going to look at is what is the triple point. No, actually the first thing we need to look at is what are we going to draw for our scale. And we're going to put temperature on the horizontal, the X, and that's in Kelvin. And we're going to put pressure on the vertical in atmospheres. And again, the scale here, if we're starting at 0, the hashes here are going to be 25, so we're going to go in increments of 25 for temperature. So it'd be 100, 200, 300, and 400. 300 and 400. That gives us enough. And then on the pressure, we're going to go up by tenths. So 1, 2, 3, 4, 0.5, 2, 3, 4, 1 atmosphere, and the top line will be 1.5 atmospheres. Okay, so the triple point is the point at which the three lines will converge. That's where all three states of matter exist together. So you've got solid, liquid, and gas all existing, all transitioning from one to the other all at the same time. And we've got this at 0.06 atmospheres, 274 Kelvin. So the 0.06 is the tricky one. It's going to be a little bit low, a little bit below the first line, and it's going to be just shy of the 275 temperature. So we're going to put it there. And then the melting point, which would be at 1 atmosphere, is 273. So that's going to be along this line, just a little bit to the left of the triple point. And the normal boiling point, which is 1 atmosphere, is 373. So that's going to be up close to this line. Okay, and then we're going to draw the lines essentially connecting the dots here. So we'd have a phase line like that, a line like this, and then another line here. The other part you have to remember is what's the solid, liquid, and gas. Kind of, if you think it through, it makes sense that lower temperatures, which is on the left, is going to be the solid. Higher temperatures on the right, that's the gas. And then in the middle, you've got the liquid phase in between the two. So a point of sublimation here would be, sublimation is the transition from solid to gas. So that could really be anywhere on this line down here. This line segment represents the transition directly from solid to gas. So anywhere along that line would be a point of sublimation. All right, interpreting a solubility graph. What is the maximum amount of potassium nitrate that we could dissolve in 200 grams of water at 50 degrees Celsius? Potassium nitrate at 50 degrees Celsius hits right here, which means you could have 80 grams, and this is per 100. So 80 grams in 100 grams of water equals how many grams in 200? As we have 200 grams of water, that would be 160 grams of KNO3, potassium nitrate, that you could dissolve there. How many grams of water would you need to make a saturated solution of 240 grams of sodium nitrate at 10 degrees Celsius? Here's the 10 degrees Celsius. Sodium nitrate is the line close to the top. It intersects at 80 grams, which means you could have 80 grams in 100 grams of water. So therefore, how many grams of water would you need to get 240 grams of sodium nitrate? And the answer there is it would take 300 grams of water, 3 times as much. One of the salts in the diagram is exothermic when dissolving. Identify the negative heat of solution. Okay, so if you notice, most of the lines on this graph have a positive slope, right? They go up from left to right. Most of them do. The ones that don't are ammonia and this cesium sulfate down here. The negative slope tells you that as you increase the temperature, you actually decrease the solubility of that substance, which is contrary to all of the other substances on this chart. The reason ammonia has a negative slope here is because it's a gas, so it has the opposite relationship between solubility and temperature that most of the other things do. Increasing temperature decreases the solubility of ammonia because it's a gas. Cesium sulfate is exothermic as it dissolves. Okay, it has a negative heat of solution, which means it's releasing heat. If you heat up the solution, that's going to hinder the effect of the negative heat of solution. Okay, it's going to favor actually not dissolving, and this gets a little bit into equilibrium, which is part of the next unit. But basically, if you increase the temperature, the system is going to respond by trying to lower the temperature, and lowering the temperature in this case means slowing down the solvation process because that also releases heat. But anyway, again, the two reasons you have negative slope, one would be a gas, the other is that it's an exothermic process. Those are kind of the two explanations for negative slope in a solubility chart. Calculations. 56 grams of an unknown substance, molecular compound. That means, just first thing to point out, molecular compound, I is going to equal 1 when we get to our formula. We're given the we're given the amount of compound, we're given the volume of water, we're given the freezing temperature, and we're asked to find the molar mass. When you're given this type of situation, you have to work backwards from the colligative property, which is the freezing point depression, and it takes 3 steps to do that. First step is use the freezing point depression formula to find the molality, because we've got I, we know how much the freezing point went down, and we know Kf, the freezing point constant, is 1.86, or negative 1.86. So the change in freezing point was negative 7 degrees Celsius. That's how much it went down. We said that I, because it's a molecular compound, equals 1. Freezing point constant is negative 1.86, and we're trying to find molality, M. Well, it comes out to 3.76 molal. That's the concentration of the solution. So that's step one. Step two is using the molality to find the number of moles. Molality equals moles per kilogram. Well, we know the number of moles. We know the molality. We know the left-hand side of the equation, and we know the kilograms because we know up in the question, we know we've got 300 milliliters of water, kilograms of solvent. So 3.76 equals the number of moles divided by 0.300 kilograms, which means that the number of moles is equal to 1.13 moles. So the last step is knowing that the number of moles equals the number of grams divided by the molar mass. We have now the number of moles is 1.13. We were given in the original problem that the number of grams is 56. So now we're trying to find the molar mass. We solve, and 56 divided by 1.13 tells us that the molar mass of that compound is 49.6 grams per mole. Okay, given some data, make some calculations. What is the molarity of the solution given here? Well, molarity is moles per liter. We need to find first the number of moles of sodium chloride. We were given 25 grams. The molar mass of sodium chloride is 58.4 grams, which means we have 0.428 moles, and that's per liter, but we don't have 1 liter. We have 83 milliliters, which is 0.083 liters, and that gives us a molality of 5.16 molar. The molality, slightly different calculation because we're talking about kilograms of solvent. So molality equals moles per kilogram. We just got the number of moles in the previous problem. Number of moles is 0.428. Number of kilograms of solvent. We're not directly given the mass of water, but we're told that the mass of the solution is 85 and the mass of sodium chloride in the solution is 25. So that means the water has to be 60 grams, right? The difference between 85 and 25. So that's 0.06 kilograms. So 0.428 divided by 0.06 is 7.13 molal solution. What is the percent by volume? Well, the volume of the salt is the difference between the volume of the solution and the volume of the water. And so the volume of the solution is 83 milliliters, and the volume of water we just said was 60 milliliters, which means the volume of the salt is 23 milliliters. 23 milliliters divided by the total volume of the solution, 83 milliliters times 100, means that the percent by volume is 27.7%. Find the percent by mass. Percent by mass, we're going to take the mass of the salt, which is the 25 grams. We're going to divide that by the total mass of the solution, which was given to us as 85 grams. We're going to multiply that by 100, and that gives us a percent by mass of 29.4%. So the mole fraction is the moles of solute divided by the moles of solute plus moles of solvent. So the moles of solvent is the 60 grams of water we had divided by the molar mass of water, which is 18, and that gives us 3.33 moles of water. So we're going to add those two together. 0.428 plus 3.33. Divide all that out, and we get a mole fraction of 0.113. And finally, what is the theoretical boiling point of the solution? Well, the change in boiling point is the I times the boiling point constant times the molality. The molality we had, first the I, the Van Hoff factor. Since it's a salt, it's going to dissociate, and it's going to dissociate into two parts, sodium and chloride. The boiling point constant is 0.512, and the molality, which we had on the previous page, is 7.13. We multiply it all out, and we get the change in the boiling point of 7.3 degrees Celsius. And that means that since water normally boils at 100, we're going to add the 7.3, and we get a boiling point of 107.3 degrees Celsius.